No.
Okay, there we go. Can you see it now?
Yep.
There we go. All right, so today, my name is Yannick Roberts, and today I'll be presenting a paper called Supervised Video Interpolation using cyclic consistency. Here are the authors. I'm not going to enumerate through them, but you could check out the course website for the paper and download it and check it out if you're interested in it. Okay, so overview. Here's what we'll be talking about. We'll be going through the frame interpolation process. We'll be speaking about interpolation techniques, common interpolation implementations, then the limitation on these implementations. Then we'll be going over the motivations that the paper is going through, the methodology that is proposed, implementation details, experiment results, and then I'm going to finish with a conclusion and a video at the end of it all. Okay, so what is frame interpolation? Frame interpolation is a process of generating an intermediate image with respect to two sequential frames in an attempt to make an animation more fluid, to compensate for motion blur, or to generate slow motion effects. So here we have two successive frames, and what we're trying to do is we're trying to generate a proper image that cohesively transitions between the poses of these frames. What are the possible techniques to accomplish this? Well, the techniques are categorized. It falls under two categories: Eulerian and Lagrangian. For Eulerian, Eulerian method considers that each consider a change in color or value of each individual pixels, and the Lagrangian method models pixel motion as spatial displacement. What are the benefits of Eulerian? Well, it's fast to compute and it's easy to represent pure surfaces. What are the issues with Eulerian? Well, thing is, you're using a grid-based implementation, and this could cause numerical diffusion, or this is also known as blurring. And what are the benefits of Lagrangian? Well, it's resolution independent, so you could have high resolution transitions between pixels, and it's also provides fluid motion. And what's the cons of the Lagrangian? Well, it's difficult to maintain cohesive neighboring pixel values. That's really computationally expensive to compute, and it's also artifacting. So when you have large pixel motions, you're gonna have a lot of artifacts. Um, Here is an example of the three common interpolation techniques. You have frame sampling, frame blending, and optical flow. Frame sampling literally just samples a frame and tries to generate based on the frame rate. So if you need 2 frames, it samples 2 frames. If you need 60 frames, then it samples down and upsamples frames up to 60 frames per second. Frame sampling is basically a crude version of Eulerian. Then we have frame blending. What frame blending does is it provides a linear interpolation between pixel values, and this is also considered an Eulerian technique. As you can see the blurring being achieved, like I said, because of the gray effect. And the last one is optical flow. Optical flow tries to determine the motion of pixels, and as you can see, not here, but in the previous video, you can see the artifacting that's occurring because of the large pixel motions. You can also see that the optical flow is a lot smoother than either values. The frame sampling is kind of stuttering, and frame blending isn't so great either. Most modern techniques rely on optical flow. State-of-the-art techniques all of them rely on optical flow. So, and the paper uses optical flow. So we'll be covering that in more detail. So, what is optical flow? Well, think of optical flow as vectors which describe the motion of individual pixels through a short time period. Um, we call these vectors flow vectors, and current state-of-the-art interpolation techniques parameterize these flow vectors through time and warp the corresponding pixels to perform an image interpolation. Now, what it means by warping is just translating an image value from one location to the next. Common variation of optical flow include Lucas-Canade method, and you also have the Horn and Schnuck method. As most optical flow methods rely on global optimization to resolve matching ambiguities between neighboring pixels, it's extremely difficult to parallelize and therefore taxing on computing. So it's really difficult to run this type of network on a computer. OpenCV has a few of these libraries, a few of these implementations, and it takes upwards of 2 seconds to generate an interpolation, to generate a flow vector for an entire image. Then there's two different types of optical flow, two different categories. There's dense optical flow, which attempts to generate an optical flow vector for an entire image. And also, I'd like to say, this is Sintel video, which is being used for the training process. And then there is sparse optical flow, which attempts to generate flow vectors for subsections of an image. Here you can see that it's only generating flow vectors for individual vehicles and not for the entire frame. So how is optical flow used to generate interpolated images? Well, here's an overview of a simple network. You have 2 input frames that you'd like to interpolate between, and you're going to have a flow estimator, which calculates your flow vectors, which could be described as here, and then you're going to parameterize these flow vectors to get the location, the pixel location where you would like to interpolate to, and then you're gonna perform spatial warping, where you're gonna transfer these pixel values to their correct location, and you're gonna have a final output interpolation image. The issue with this method is there's a lot of artifacting with large range or large motion, so we'd like to compensate for that, and this is where the bidirectional flow guide interpolation techniques come into play. And what this does is, instead of just using one directional flow vectors, you're going to use flow vectors going both back in time and forward in time. So you're going to still use 2 input images, but your flow estimator is going to, this flow estimator basically calculates the flow vector forward in time. This one calculates the flow vectors backward in time. And what you're going to do is parameterize these flow vectors, get your location, you're going to warp the location, and then you're going to get 2 output interpolated images. What you need to do now is blend these 2 interpolated images to get a final result. Now, the paper utilizes a network called Super SloMo, which is described here. What's happening in this network is you're going to have your 2 images, and the flow vectors are calculated using this UNet right here, and the output is being fed into this other segment of the network, and this section. Okay, so this section linearly computes the combined. Okay, this section computes the targeted timestamps to approximate where your flow vectors are going to be, and then to compensate for artifacting, there's another U network to mitigate artifacting, as I said. And then you're going to output these artifacting, and this section right here does the warping, and you have your output image right here. Okay, so limitations on using CNNs to train, on using basically a SloMo network to train on higher resolution images. Well, because it's a supervised method, it requires a lot of high frame rate data, and it's really expensive to collect these data, and it's also expensive to store this data. Another limitation is domain retargeting. So say you train your network in a high frame rate data of this road that's in front of an ocean, and you use passing, say, a slow or low resolution data of a shark in an ocean. That's going to have difficulty interpolating because it's not trained for this type of domain. It's only trained for high frame rate domains with roads in front of oceans. And finally, another limitation is there's still issues with artifacting because of fast, high-speed motion. I'm sorry, that's really loud. Okay, so there's still artifacting because of high-speed motion. Here you can see as the feed gets occluded, there's a lot of artifacting, even more than if it's just movement. All right, so how do we deal with this? Well, the author sought to present an unsupervised approach for synthesizing high frame rate videos from low frame rate videos. And this is an entirely unsupervised approach which trains on low resolution images, on low resolution videos or low frame rate videos. So how is this done? Well, given a triplet of consecutive frames, 2 intermediate frames are generated between the 2 consecutive frames, which you see here. So we're trying to generate 2 intermediate images given a triplet of frames. And the paper goes on to label these frames I1 for the first frame, I2 for the center frame, I3 for the final frame. And then you're going to have the intermediate frames, which is interpolated using the SloMo model. And then you're going to also, so what you're going to do next is you're going to interpolate between these center frames. So here we interpolate between the previously interpolated frames, and we have another frame. This is the center frame, which is labeled I hat sub 1. And from here, we're gonna design a loss function. This loss function basically relies on something called cycle consistency. Cycle consistency could be understood in terms of a cycle consistency GAN. What a cycle consistency GAN does is it generates some output given an input. So say you're given an input image, you're going to generate an output image, and from that output image, you're going to use another GAN to regenerate that input image. So right here, utilizing a cycle consistency loss. So you're relying on the cycle consistency loss to converge these two parameters or these two GANs. So what we're really doing for the cycle consistency loss is we're taking that third image that we've generated, and we're going to find the L1 distance between the ground truth center image and the generated center image. Okay, so here's a high-level overview of what's going on. Our input images our ground truth input images are marked in green, and the time between frames have been normalized to 1. So this is going to be 1 unit, and this is going to be another 1 unit. And from these from these frames, you're going to generate an intermediate frame. So you're going to generate 2 intermediate frames, and from these 2 intermediate frames, given the timestamp. So here's our model. Model is basically the interpolation network, and we're going to pass in okay, so we're going to pass in the first consecutive image, which is I0 and I sub 0 and I sub 1, and we're going to give it a time parameter. We're going to also pass in a second set of parameters, I sub 1 and I sub 2, and we're going to also give it a time parameter, which should be equal to the first time parameter. And what we're going to do is we're going to pass in this, we're going to generate our first set of intermediary frames, and we're going to pass that into the model again to generate the third frame. And from this third frame, we're going to use our consistency loss to force the network to convergence. In addition to the cycle consistency loss, we're also going to use a pseudo supervised loss. What the pseudo supervised loss does is it forces the networks to regularize, which is basically injecting semantic details into the network, so that say something's occluded or something's hidden behind a wall, with the semantic knowledge that's being learned in the network, it's going to remember these details and try to correct it. So we're going to pre-train a network. And in this paper, they pre-trained the same network, but the SloMo network, but they used ImageNet. Oh, I'm sorry, they didn't use ImageNet. They used a few other networks from other domains. So we're pretty much going to train this network on just a set of random videos. It doesn't have to be videos pertaining to our exact domain, and this allows for domain retargeting, which, as I said, you train a video on a set of images, on a set of frames, and you're trying to learn from a totally different scenario. So we're taking in, for the pseudo supervised loss, we're taking in the first consecutive set of frames, and what we're going to do is we're going to we're going to interpolate between these two frames, and we're going to find the L1 difference between this interpolated results and interpolated results of our initial network, or the network that we're trying to train. That's the non-pre-trained network. This is done for both the first consecutive set of images and the second consecutive set of images. So here's a high-level overview of the network that's being proposed. Here's our triplet images. Here's the first consecutive images. Here's the second consecutive images. And what we're doing is we're passing the first consecutive images into our pre-trained network, and we're going to generate a pseudo loss from this set of images. Same, we're going to pass our first set of consecutive images into our base interpolation CNN. We're going to generate what's our intermediary frame, and from the intermediary frame, we're going to generate another set of intermediary frame from the second set of consecutive images. And from these images, we're going to pass it again through our base network, and we're going to generate, then we're going to take the cyclic consistency loss between these generated images and the center image. And we're also using two pseudo consistency loss. So here's our primary objective function. As you can see, we're using the cycle consistency loss, and it's parameterized by both I hat, which is the generated center frame, and the ground truth center frame. We're also using the pseudo supervised loss, as you saw in the previous slide. Here are both of them, and what we're passing in is the first set of consecutive images and a time stamp. And we're finding the loss between this set of images and what's being generated from our pre-trained network. This is done for both the first consecutive set of images and the second consecutive set of images. We're also using our cycle consistency weight to kind of control what's the extent that the cycle consistency loss provides, and we also have a pseudo-supervised weight. And these pseudo-supervised weights are ramped to enable, these pseudo-supervised weights are ramped to emphasize the parameters of the base cycle consistency network. All right, so here's our final loss function. We're using a primary objective function, which is what I've just described. And then there's also these additional terms. You have a perception loss. A perception loss is basically we're passing in the center frame into a VGG16 network, and the VGG16 network has been pre-trained an ImageNet, and we're taking the fourth consecutive, we're taking the data from the fourth consecutive layer, and we're finding the L2 loss between this data, the generated data, and the ground truth data at this layer, and we're just adding it to our entire loss network. We're also using a warping loss. What a warping loss does is we're taking an image, say I sub 0, and we're warping it towards I sub 1, which means we're trying to generate I sub 1 from I sub 0 using our SloFlow network. And from this network, we're going to find a difference between these two values, and this difference is going to blend to the loss of the entire network. We're finding for all the images that's being generated in the scene. Also, we're using a smoothness constraint, and this smoothness constraint ensures neighboring optical flow values maintain similar values. So, like I said, it's really difficult to compute neighboring values when you're using optical flow, so this kind of regularizes the entire process. So now let's go to data matrix. Here's a data set that's being used. We've seen a few of these data sets already. For the SloFlow data set, that's actually behind a paywall by NVIDIA, so it's not accessible to the public, but the authors also use the Cintel and Adobe data sets. And what the Adobe 240 data set is, it's 100 images, which is 380 frames, and it focuses on real world scenarios. And all the frames are annotated with bounding boxes and labels with 9 attributes. And these attributes could be from occlusion to movements. It's just generic labels. It's not really specific. And for a Centel dataset, this is an entirely computer-generated video using Blender 3D. There are 13 videos, 560 frames, and it's being computed up to say 1,000 frames per second. Okay, so here we are. For training for our supervised section of the network, we're going to train on the Adobe 240 frames per second dataset, and we're also going to train on the YouTube 240 frames per second dataset. And I must have to say, the YouTube 240 frames per second dataset is also real world events. For the unsupervised training, we're going to use Battlefield 1 dataset, and we're also going to subsample the Adobe 240 frames per second dataset into 30 frames per second. Okay, so what evaluation methods does the network uses? Well, it uses peak signal to noise, structural similar image metric, and interpolation techniques. We've seen peak signal to noise already, and we've also seen structural similar image metrics, but we've never seen interpolation error. And what this is it's just a root mean squared error between the real world, the ground truth image, and the interpolated images. And so this, because this is an error value, the lower the value, the better it is. Not unlike peak signal to noise or SSIM. All right, so here's a low resolution unsupervised training results. What they're trying to do is they trained on, okay, so they've trained on the low resolution images on the lower resolution data set, and then they're going to try to generate center frames on the UCF 101. They're really trying to generate the center frames. Like they're going to take 3 frames and they're going to generate the center frame out of those 3 frames, and you're pretty much just finding the difference between the center frame and what's being generated. And as you could see, the proposed method actually performs almost as good as the baseline method, which is expected because it is using the baseline backend for its generation. All right, so now for the domain gap testing. What is being done here is we're taking 9 frames and we're trying to generate the 7, and we're trying to interpolate 7 internal frames between these 9 frames. So this network's being trained on slow flow, which is 240 frames per second. And what we're doing is we're going to divide slow flow into 2 categories: a 30 frames per second set and a 240 frames per second set. We're also going to use the Centel data set at 30 frames per second. And here are the results. Oh yeah, and I forgot. Okay, so the trivial copy, what we're trying to do is instead of generating an intermediary 2 frames to generate the 3rd frame, we're just going to skip the intermediary section. We're going to generate the 3rd frame directly. And this method's actually a lot worse, or produce worse results than generating the intermediaries frames. And that's because the network's actually challenged. The paper doesn't really go over it, but I'm thinking the network is actually challenged to with the semantic details. The semantic details of, say, of using 2 frames going to the 3rd one. You're trying to learn the 3rd frame, and you're also trying to learn the 2nd frame. So there's a lot more to learn in that process. Okay, so the trivial results, you can see we are using a PSNR of 25, 0.75 SSIM, and 14, which is really terrible. Now the baseline, they're using super SloMo for this baseline network, and we're getting a PSNR of 32, 0.887 for SSIM, and IE of 6.67. And for the proposed network, we're using, it's divided between cycle consistency, between just the cycle consistency loss and cycle consistency loss added with the pseudo supervised consistency loss, or loss. Anyway, so with just the cycle consistency loss, we're almost equaling that of the baseline method, which is expected because we're actually using the baseline as our network. For the proposed method, with the pseudo consistency loss, we're actually gaining a significant jump in our output values. And this is because the pseudo consistency loss is trained on a totally separate domain of video. So when you're introducing that added data to our network, the network is able to use these values to hone basically the results. Here for this one, we're using both Adobe plus the YouTube datasets, which is a significant significantly added amounts of frames. And for our baseline network, we're doing 33.13 when we're also training using Adobe and YouTube, and we're trying to test on slow flow. And for our proposed network, we're getting 33.2, which is also pretty high compared, pretty high just because of the added pseudo supervised loss. Okay, so for this one, these results we're training Adobe and we're testing in Sintel. And Sintel is a totally computer generated results, and Adobe is a real life, real scenario kind of result. So this is a prime example of domain retargeting. And as you can see, the proposed method presents a significant gain over the baseline method. And this is 100% due to the pseudo supervised method. And similarly, when we're using the Adobe plus the YouTube video, we're still getting a significant amount, although the baseline method is able to compete with the proposed method. Okay, so for these results, what we're using here is on the left, we train at quarter resolution and test at full resolution. And as you can see, the results are better for the proposed method than the baseline method. Similarly, on the right, we're training on UCF 101 using the deep voxel flow networks instead of the super SloMo network. And as you can see, the results of our network fine-tuned in the deep voxel flow network is a lot more than just using deep voxel flow. So here are the qualitative results. You can see right here, there's a lot of, the guy's torso is a lot more defined than this one, which is the baseline method. And also the helmet's the edges are a lot more detailed than the baseline method. So this proves that the network's retaining a lot of semantic details because of that pseudo pre-trained network. So ablation studies. Here they're trying to compute the optimal weights for the pseudo inverse network, and as you can see, we're losing values as we increase the pseudo weights, pseudo supervised weights. But ablation here, the optimal weights. Now here we're trying to find out what's. Oh, I'm sorry. Okay. My computer just froze. It's my computer keeps freezing. I'm sorry about that. I'd like to touch on the conclusion. So we presented an unsupervised learning technique for synthesizing high frame rate video from low frame rate data. The paper also models trained with the technique is able to synthesize arbitrarily intermediate frame comparable to that of state-of-the-art supervised approaches. The technique could be applied to reduce domain gap in video interpolation, and the results presents a potential in learning to interpolate high frame rate videos using only low frame rate videos. And finally, here is the results of super SloMo. As you can see, this, even with occlusion, it's able to maintain the finer details or the objects in the scene, and you're not seeing much artifact. Similar with this video. And this is just using the super SloMo results. I could not find any results for super SloMo added with the cycle consistency loss. And that is it for my presentation.